So I'll talk a little bit about what spectroscopy is and why infrared is good for determining functional groups. So we'll review that today. Just starting off with the basic sort of elements you need for each functional group and how IR is really good for determining oxygen. So that was the crux of mass spec. We know that if there's an odd mass for the parent, there's an odd number of nitrogens, and then with chlorine and bromine, there were these signatures in the mass spec. And oxygen was the heteroatom that was a little bit more challenging. So we'll look at IR spectra and how that can tell us if there's an oxygen in the molecule and what functional group is present in. So there's two things. There's like a PowerPoint itself. You can sort of click through with animations of what IR is. And then I made a screencast of that when I'm talking through these different things. So we'll talk about electronegativity, how you assign a dipole to a bond, and then what actually is a bond. So we'll review that again. The infrared experiment, really, we have to understand the fundamentals of what a bond is. So we'll look at a curve where two atoms come together, they're far apart, they come together to form a bond. And what is the nature of a chemical bond? Any questions before we get started? So the question is, how can we know if oxygen is present in the molecule if there's not a specific signature in mass spec? So we're going to learn about IR spectroscopy. And spectroscopy is the interaction of light with matter. So light is kind of weird in the sense it acts as a wave and a particle. So it's this duality. And if you go into physics or physical chemistry, you'll learn more about that. But it's an important topic if you're going to take like the MCAT or the pharmacy or vet exams. You'll have to know this pretty well. So IR spectroscopy is used specifically to identify functional groups, and I'll just abbreviate functional groups as FG. And so there's about 15 functional groups that you need to know the names of. We'll review those today and how IR can tell us if they're in a molecule or not. And so an FG is a specific bonding arrangement of elements. And so if I write COH, we should know that's an alcohol. And using the periodic trend of electronegativity, we can say that the oxygen is more electronegative than the carbon. So that's just assigning delta plus, delta minus. And from that, we know it's a polar covalent bond, and now we can draw a dipole moment. And so the dipole moment is a vector. A vector is something that has a magnitude and a direction. So we sort of use the plus sign, and then we draw an arrow to the negative sign. So the dipole moment of that bond would point towards the oxygen. And the infrared experiment, the light, the IR light, when you shine it into the sample, it's detecting those bond dipoles. And when we talk more about the bonds in a little bit, bonds are not static. So we report a bond length. That's the average of the movement of the bond. A chemical bond you can think of as a spring. It's moving back and forth, always. Even at absolute zero where there's no heat, there's still energy. It's called the 0 point energy. So the bond dipole moment arises from the difference in electronegativity between the two elements. And when you have molecules with a lot of different functional groups, that's what makes the spectra a little bit complicated to interpret. And so remember that in our periodic table, electronegativity increases towards fluorine, across the period, and then up the group. So that's a way to remember how you assign this delta plus, delta minus. And so what I want to frame IR in terms of that problem we ended on last week, where we were looking at a parent ion of 72, and we went through some calculations and said that this could be C4H8O, and therefore it has 1 degree of unsaturation. So the spectrum that you see, that's a typical IR spectrum. The x-axis is called wave numbers. The unit of that is called reciprocal centimeters. So this -1, if you remember from physics or algebra, so that means 1 over centimeters. The unit is kind of weird, and it's just historical of how the experiment developed. We're not going to get too much into like the math of this, but it's called wave numbers. The y-axis is transmittance, and typically it's percent, so 100% to 0%. And so we're just going to read the thing from left to right. And so if you're starting here and you're reading that way, see how it's not exactly 100, but it's close enough. So what that means, if you look at that wall, you see that green laser light over there. So that's 100% transmittance. You can see it. So when I put my hand into it, you don't see it anymore, right? But it's on my hand. So my hand is the sample. And so that right now is 0% transmittance. If my hand is the sample, that means at that wave numbers, the molecule is absorbing that light. And so when it absorbs it, you start seeing it dip down towards 0. That means, so we can call that a signal. I call it a peak. If you're from Great Britain, you'll call it a signal, where they're more formal about things. But at that region in the IR spectrum, the light is being absorbed by some dipole moment. And there's different regions in the spectrum that we're going to learn to interpret. What I first want to say is the wave numbers run from 4,000 on the left to about 500 on the right. At 1500 and below, you don't have to worry about that. So anything below 1500, you see there's a lot of signals here. And that gets really complicated to interpret, so we just ignore it for the most part. It's generally called the fingerprint region. So like your fingerprint, it's pretty specific, and we just ignore it because, as I'll explain later, the stuff that happens there is a little bit beyond the scope of this course. So there's some stuff here, around 3,000, and then there's nothing, so we call that the baseline. The baseline is there's no absorption of light. So transmittance is the light going through, and absorption is when the light is being absorbed by the sample. And then we hit this pretty significant signal here, which I've labeled 1730 wave numbers. And that's a pretty diagnostic signal. And that belongs to a carbonyl group. So specifically, we would say it's a carbonyl stretch. The IR light senses that carbonyl group in the molecule, and what it's doing is stretching the bond. And so once the IR light passes that energy, so it's absorbing as it goes down, it passes it, so it's going back up, and then it hits the baseline again. So when it dips down, that's when you interpret the signal. And so if we recognize that as a carbonyl CO double bond, that's 1 degree of unsaturation. And so if we have 4 carbons, 8 hydrogens, and 1 oxygen, 1 carbon and 1 oxygen belong to that fragment, and we've taken care of the degree of unsaturation. So that leaves us with 3 carbons and 8 hydrogens to now build from. So we can use that to start proposing constitutional isomers. So over the next couple slides, we'll review what different functional groups are, and then we'll see where they occur in the infrared spectrum. And so if they're there, we can say, okay, we have this little bit of information for proposing isomers. If it's not there, then you can totally say, okay, it does not have an alcohol, it does not have a carbonyl, or whatever. So what functional groups have a heteroatom bonded to hydrogen? So this would be N, O, or halogens. So alcohol is typically OH. Carboxylic acid, I'm just going to use the little squiggle to say that's the rest of the molecule, and alcohol just means OH. Carboxylic acid has a carbonyl that's bonded to an OH. Does an ester have a hydrogen? I see someone saying no. So the ester, that eliminates A. What about choice B? Are all of those valid? See some head shaking, no. The tertiary amine is not. So this would be a primary amine. This would be a secondary amine. A tertiary amine would have 3 carbon groups to it, so it does not have an NH bond. So for C, we've already seen the secondary amine and carboxylic acid all have OH or NH. A tertiary amide does not have an NH. So an amide is a carbonyl bonded to a nitrogen. Then if it's tertiary, the other groups are carbon, so there's no NH there either. So that's going to leave us with D as the correct answer. So what this is telling us is that in a specific region of the IR, you're going to see OH stretching and NH stretching. We already agreed that every molecule has carbon-carbon bonds and carbon-hydrogen bonds. So carbon-hydrogen stretching is not really diagnostic for IR because every molecule has it. So what about triple bonds? What functional groups have triple bonds? So A, remember an alkyne is a carbon-carbon triple bond, and a nitrile is a carbon-nitrogen triple bond. There is something I want to point out for the alkyne. The alkyne has to have a CH bond. It has to be a terminal alkyne. And the reason for that is if you have an internal alkyne where now both carbon atoms are bonded to other carbons, that triple bond has a really small dipole moment. And so the IR spectrum can't, or the IR instrument can't detect it. So you need to have an H on one carbon and then a carbon on the other. So what functional groups have the carbonyl associated with them? I think I heard someone say C. I had tubes in my ear as a kid, so my hearing on this side's a little bad, but I picked up C. So C is the right answer. An aldehyde, the carbonyl is at the terminus of the chain. An ester, again, it's at the terminus, but you have this other carbon group bonded to that oxygen. And then a ketone, the carbonyl is in the middle of the carbon chain. If you remember from Module 1, we learned that there's a lot of functional groups that have carbonyls. So the question or the problem now is, if all of these have carbonyls, how do I know if I see a carbonyl stretch which functional group it belongs to? So this is where it's visual. The carbonyls might move a little bit in the region they're present in, but some of them are going to look very different, and they're unique to what functional group they're a part of. So now this one is asking a carbonyl group now bonded to an oxygen, and that can be bonded to something else. So for A, we already know an acid and an ester work. An amide is not valid because that doesn't have oxygen, it has nitrogen. Looks like B as in boy is going to be the correct response. An anhydride it's called an anhydride because it's the condensation of two acids where you lose a molecule of H2O or water. Carboxylic acid. And then the ester has the carbonyl with the oxygen bonded to another carbon. So B is correct. C is wrong because the acid chloride has a chlorine. And then D is incorrect, again, because we have amide. So same sort of question. Carbonyl now bonded to nitrogen. Again, these were called amides, so A is the correct response. B we saw in the prior slide. C has a carbonyl bonded to a chlorine. And then D was just the carbonyl at the end of the chain with an H bonded to it. So as a review, again, I like to think in terms of food. I'm always hungry, trying to shove something into my pie hole. There's like layers of lasagna here of learning. So you see these words, alcohol, that's the functional group, and then they're represented sort of with letters that have the elements required to be in them. So here's your functional group. So which response would best match the functional group with sort of that line way of drawing the elements in it? I think I heard C again. So C, alcohol has OH. Amine is going to have, so that would be a primary amine. And then the acid is going to have CO2H. So, when we say the word alcohol, you really need to think of, okay, it has an OH in it. And then what is the Lewis dot structure of that? And then ultimately, when you see the IR, how do you know it's there or not there? So amide, alkyl chloride, so notice that's not acid chloride, and then acid chloride. I think I heard an A. What can be confusing about reading like RCONH2? Again, you have to expand that into the Lewis dot form. So that would be R. That's what CO means, carbonyl. And then NH2. So if you tried to interpret that as like RCONH2, RCONH2, that would be wrong. So again, it's always going back to the stuff that we already learned in terms of how we're putting our sauce, noodles, cheese down in the lasagna. So organic chemistry really is about recognizing patterns, and in the patterns you can figure out the reactivity of the functional groups. That's why you'll see this abbreviation R a lot, because if we're just talking about the amide, it's just that collection of elements in the R part, the rest of the molecule R is just coming along for the ride. And so what's the point of these questions? Essentially what we just did was classify each functional group according to single, triple, and double bonds. We said every molecule has CH stretching, so every IR that you look at, it's going to be there, but it's not going to tell you a whole lot. Amines and alcohols, they'll show up pretty prominently, and they'll have a unique signature or shape to how they look. Triple bonds, the terminal alkyne and the nitrile, they occur in another region, and they're not as intense. So we'll talk about these words: broad, sharp, dull, things like that, just in terms of how the shape of the signal looks. Double bonds, the alkene double bonds sort of fall below 1500, so we just don't worry about them. The carbonyls are pretty prominent though. And we saw all these functional groups with carbonyls, and for the most part, they all look different. So once you sort of memorize the shapes, you'll be able to say, okay, this belongs to a carboxylic acid, this belongs to a ketone, this belongs to an amide. And so as we interpret IR, we can say, okay, from this signal, I know I have an amide. The mass spec is odd, so that confirms the presence of a nitrogen as well. And ultimately, we're trying to suss out what functional groups are present. So it'll give you a broad idea of what some of the elements are in the molecular formula, but it's not really telling you how they're connected. And for that, that's you'll have your second exam starting Wednesday, which is on mass spec and IR. The rest of the module is on NMR, and NMR tells you exactly what carbon is bonded to what carbon, how many hydrogens are attached to each carbon. So that's how we're drilling down into getting more specific about what constitutional isomers can arise from the data we see. So there's 4 regions, including the fingerprint region. Again, we're going to ignore that. Region 1 is what I'm calling XH stretching, so single bond stretching. Your normal alkane, everything has that, so it's not incredibly diagnostic. Alkenes, those have an sp2 hybridized carbon H bond, so sometimes those are a little bit more prominent. We could say, okay, there's a alkene CH. The terminal sp hybridized carbon H bond of an alkyne, you'll be able to see that pretty prominent. Then we have amines. Again, this is for only primary. In secondary amines, tertiary amines don't have that NH. And then alcohols will always have an OH stretch. So these are presented to you, as you're reading the spectrum from left to right. Region 1 occurs first, then region 2, then region 3. Region 2 were your triple bonds, nitrile and alkynes. Again, this has to be terminal. If it's an internal alkyne, again, the dipole moment's really small, and the IR light will not detect it. And then finally, region 3, your double bonds really focused on carbonyl groups. So aldehydes, ketones, carboxylic acids, esters, anhydrides, acid chlorides, and the different amides. Again, there's 9 carbonyl containing functional groups. If you're thinking, well, how will I know what that stretch belongs to? There's a little nuance to each of them that differentiates them. And so how does this even work? So here's the electromagnetic spectrum. So EM spectrum. And if we're thinking of light as a wave, this first part here, so spectrum means, there's sort of a start and a stop point. That's different from a continuum that goes on for infinity. But if we start to the right, you see the wavelength is really long. So wavelength is measured from like crest to crest, or trough to trough. And so that's a really long wavelength, and so it's lower energy. And then to the left of it, you see the wavelengths get smaller and smaller. And so this is higher energy. And then down below that are the different types of light. So there's radio waves. That's what, AM, FM radio. Submarines use long wavelength radio to communicate. Then microwaves. That's, sticking your popcorn in the microwave and getting it to pop. IR. So IR is infra. Infra means before. So infrared. And as you see, when we get to the visible region, it's before red. So here's our red. So there's Roy G. Biv. That's how you remember the rainbow, right? So of the electromagnetic spectrum, we as humans only see in the visible region. Ultra means sort of more or after. So once you scan from red up to purple, you get to violet. So ultraviolet, that's the sun rays. You can get sunburnt if you stay out in the sun too long in the summer. So it's higher energy. The normal white light coming from the ceiling is a mixture of all the wavelengths. If you have a prism, it'll separate it out like Isaac Newton found. Then X-rays, and then cosmic and gamma rays. All of these things are used in spectroscopy, and they all give different pieces of information. So we're talking about IR, and what IR light does in a molecule, it vibrates the bonds. And there's different sort of subcategories of vibrations. When we get to NMR, NMR uses radio waves. That acts differently on the molecule, and so you detect different things. We don't talk about microwaves at all. If you take 256 next semester, we'll talk about ultraviolet visible spectroscopy. Like my shirt is like a blue color. Like, why is it blue? How do you perceive it as blue? So that's shoved off into next semester. So what is a bond? This is a pretty standard curve that you'll see when learning about chemical bonds. On the x-axis is the distance between the two atoms that are coming together to form the bond. So you can think of this over here as infinity. So you have two atoms of hydrogen coming together. They're each going to supply one electron to form a bond. So they're really far apart. They exist, but they're not aware of each other. And as they go more towards the left, they're getting closer and closer. So eventually they're attracted to one another. And at some point, they do form a bond. And so on this x-axis, in Module 3, when we start talking about bond distances, we report like a single number. But again, the bonds move. Everything has energy. And so the bond is not static. It's constantly moving. And so the distance is the average of how far it can move before it like breaks apart. And so if you go up from the x-axis over to the y-axis, which is the energy of the bond, we'll talk about average bond energy. So if you put enough energy into the bond, you can then break the bond. But what this curve is telling you is that within that region of the curve, you have distances and energies. And so as part of that, when the light excites the dipole moment, it's like stretching it, or it's doing other vibrational modes. And so depending on the energy of the light, it's going to excite one of those modes. If you get too close together, there's repulsion, and that's not good. That's real high energy, right? So as you go up this curve, the energy increases. So that's like your normal human relationship, right? You find your significant other, you move in, maybe they leave the toilet seat up, maybe they don't flush the toilet, you start to get sick of them, you're like, get the hell out of my apartment. So you break up. I mean, that's the atoms behave like humans, humans behave like atoms. So just keep in mind when we're talking about this stuff, there's always energy involved. And so with IR, we're looking at specific ways in which that energy excites the molecule. And then NMR is different. So if you think of bonds as springs, there's different vibrational modes. And I'll explain that when we look at some data, why the signals look the way they do. The most common mode is just stretching. And so the first one is like symmetric stretching. If you imagine this is a carbon atom, these are two hydrogen atoms, so that would be a methylene group. So CH2. That's like this. They're both stretching at the same time. And so asymmetric stretching is sort of like your engine in your car, your pistons moving at different. Now, if you can imagine all of this stuff is sort of happening at once, that's why the signals on the x-axis of the IR, they span a certain width. They don't just go down and up. They go down, over, and then up. Is because they're doing all these different vibrations at once because they're in that energy well of the bond. And then wagging. So this is, you could make a exercise video of IR stretches. Oh wait, wagging is like this. Twisting is like this. So scissoring, you're chopping the paper. Rocking, you're at a rock concert. And so, again, the way this happens is you're in the well of the bond, and as the laser light, the IR laser scans over, it's exciting these different modes, and that's why the peaks sort of look messy. So, I think all of the slides that are in the handout today, we probably won't get to all of them, so we'll cover probably the more actual data more on Wednesday. So now we're just going to look at how do we read these things. And then later today and on Wednesday, we'll look at data to see, okay, is the functional group there or not? So again, the y-axis is transmittance. The x-axis is wave numbers, or another way of putting it, it's the energy. So transmittance and absorbance are inverse of one another. So notice this scale just goes to 1. So then we would just say it's transmittance. If it was 100, we would say it's percent transmittance. So as we read from left to right, there's the baseline. Nothing's being absorbed. And then it's gradually going down. And now here, there's 100% absorbance or 0% transmittance. So within that signal there is your CH stuff. So highlighted in blue is your XH, so it's CH, OH, NH stretching. And then once you get out of that region, you get into region 2, that's your triple bonds. And you see how it's flat there? There's nothing there. So this compound, whatever it is, has no triple bonds in it. So as you interpret these, you're looking for the presence of something, but you're also eliminating stuff if you do not see a signal. Region 3, primarily carbonyls. Again, there's nothing there. So we can confidently say that has no carbonyl containing functional groups. So I'll use the word radiation. Normally, when you hear that, you think of bad things, but when we say light, light is radiation, so we can use those terms interchangeably. If radiation is absorbed, then you'll see a signal. So again, within this region here, that's something's being absorbed, and so that's a signal. Most oftentimes, the signals are reported as a single number. But what you can see is that, this is spanning, say 3,000 to 2,800 reciprocal centimeters. So sometimes the data will be reported as a span of numbers. Sometimes it's just reported as a single number with the greatest absorbance. And then again, this fingerprint region, that gets pretty complicated below 1,500, so we primarily just ignore it. And so to summarize what we're looking for in each region, region 1 spans from 3,600 to 2,700. Your CH, OH, NH stretching in alcohols, amines, and alkanes. Region 2, 25 to 2,100. Triple bond stretching in alkynes, nitriles. Azide was the N3 group that we saw in AZT. Region 3, 1850 to 1600. Double bond stretching, primarily just carbonyls. The CN double bond and the CC double bonds start falling below 1600 and they actually move into the fingerprint region, which is region 4 below 1500. And that's primarily your single bond stretching, other than like CH stuff. So carbon-carbon single bonds fall in there. So you're looking to see what is present, but also what is absent. So you can look to region 1, region 2, region 3. I myself really go to region 3 first to see if there's a carbonyl. If it's not there, then you can eliminate a lot of functional groups. But if it is there, then you have all these other things to consider. So I believe the next two tables, they're more of reference, like where do the certain bond types appear, what region, what's their energies. So here are the different bond types that we know, and again, those are just in the functional groups we learned. Bond energies we'll focus more on in Module 3. The region in which those bonds occur, signal intensity and shape. So we're using like strong or weak, moderate, sharp, broad. Those will become more apparent as we look into the actual data. And I'll try to give you an intuition of, okay, what is sharp or what is broad, what's intense, what's weak. So here's your functional groups in column 1, how they're abbreviated. If you can extract out if there's a degree of unsaturation to help you with the molecular formula. The different regions, 1, 2, 3, and then what sort of signature shape are you looking for? Again, since you're taking the exam outside of class, you can refer back to this stuff at your leisure. As I posted in one of the announcements, all the spectra that you see, they're either from the NIST webbook, or there's a Japanese site, we call it just SDBS. You can stick in a molecule name and then it's going to give you all the different pieces of data. So that's where I'm getting the stuff you see here and on your exams. Any questions? So we'll It's I think it's called webbook.nist.gov. So NIST is the National Institute of Standards and Technology. Just as a side note, if you want to buy a jar of $3,000 peanut butter, you can go onto the NIST website. They make peanut butter that's like standardized for analytical testing. Do you have a question?
Would water show the same signal as like alcohol?
Yeah. So that's an issue when you're actually using the experiment, is purging water out. So typically when you do any sort of measurement, you're always doing a background measurement first. Then you measure your sample and the background is subtracted out. Because water will swamp out if you did have an alcohol in there. So this is a typical question. Here's a piece of IR data and what functional group is present. So when I start reading this from left to right, I see there's this really broad signal here. This is your normal CH looking stuff. I don't see anything really around 2000, so that's region 2, so there's like no triple bond stuff here. And then I get into region 3, I see a nice I would call that a sharp signal. Sharp because it's going down and then it hits that point and then it goes back up. So at that point, it's not really spanning a whole lot of wave numbers. It goes down and then up. I would say it's an intense signal because if you draw a line back over to the y-axis, you can see that's about 5% transmittance. So it's almost going down to 0. So it's a pretty strong functional group. Since it's in region 3, we would say that's a carbonyl stretch. And then returning back to this really broad thing here, this is an OH stretch. So those two things are actually one functional group. That's a carboxylic acid. So the presence of this broad signal plus that carbonyl indicates that it's not a ketone with an alcohol somewhere else in the molecule. Because an alcohol by itself, an OH, looks very different. So a carboxylic acid, you're looking for this this broad. When I say broad, I mean if I draw a line down where the signal starts to where it's sort of terminating, see how it's spanning quite a distance in wave numbers? So that's what I would mean by broad. And then again, this one would be sharp. So visually, that's what you're looking for. That's what, if you ran, 20 different carboxylic acids, they're all pretty much going to look like that. So this would be A. So in the acid, see how you have all this extra stuff that's highlighted in red there? That's indicative of OH for an acid. It kind of merges into the CH. So another spectrum, you have a question? Yeah, so the question was, is it just visually practicing looking at these differentiating between OH and CH? So let me explain on this slide, and hopefully that will answer your question. See all this stuff right in here? That's sort of what a normal CH region looks like. Yeah. So there's some CH stuff. Then as we scan over, we hit this next really sharp, intense signal. So that's now in region 2. So it's like 2250 inverse centimeters. So that's indicative of a triple bond. And as you scan further over this way, there's nothing in region 3. So of this, the correct choice would be D-nitrile. So that signal is telling you there's a carbon-nitrogen triple bond. And as you stack more layers into your lasagna, you could confirm that by looking at the mass spectrum where the parent ion would have an odd mass. Yeah.
Is the peak at like 3800 right there, like the evolution peak, is that significant?
I was hoping no one would notice that. One of the tough things I think about learning in this course is, like, your textbook will have really nice looking spectra. Like, what I mean by that is, like, this line would be flat and then that stuff wouldn't be there. So what you don't want to do is get too overzealous about interpreting these things. Like, yeah, that looks like it could be something, but I would say maybe that's like water. It's probably just coming along for the ride. Most of the signals you're interpreting are going to be very prominent. And so you don't want to get too far into the weeds, you know what I mean, so that you can't see the forest anymore. We're about out of time. We'll continue on with this with the rest of the functional groups on Wednesday. But your exam 2 is on mass spec and IR.